All right. So thank you, everyone. Thank you for coming for our next session. This session is a little bit different and a little bit less traditional from what we used to have in the past. In the past, a little bit of theory and the demo of the actual of the tools. In this particular case today, we're gonna go, or Anatoly specifically will go through a real case study scenario in microelectronics industry to see basically the entire process end to end of the problem solving. Now, one ask for everyone, this is a tough topic. There's a lot of material to go through. If you can, please keep the questions to the end. We will make sure that we're answering all of them as we usually do. And so, yeah, welcome to anybody who is new to this to these sessions, and welcome back to everybody who is coming back. Without further ado, Anatoly, the stage is yours.
Thank you. So let me share my desktop. Okay, can you see my desktop?
Yeah, right now we do.
Okay, great. So we will talk about electrochemistry, electrodeposition, or copper deposition in microelectronic, in semiconductor manufacturing. So this is a project within our platform, PRIZ Guru platform. Title, some information, general information, which is necessary for AI. And I just tell you a little bit about this process. You should not be a PhD in semiconductors to understand it. Very easy. Copper is used for interconnection in semiconductors to connect transistors. And it's very good. It has very low conductivity, resistivity, and it's can be deposited from aqueous solution by electrolysis. And this is very good way. What is typically done? We should create vias and trenches within the dielectric, which is a silicon oxide or some modification of silicon oxide. We should deposit tantalum, very thin layer of tantalum. And this is a barrier in order to prevent diffusion of copper inside of dielectric. And after that, a very thin layer of copper, which is a seed layer. We need seed layer in order to connect it to electricity and allow electrolysis. So we did it, and we deposit copper. Copper fills in all vias on trenches, and we built a lot of copper above. And after that, we remove it with polish. And polish is also not very trivial. We remove it in 3 steps. First, we remove bulk of copper, and there is an endpoint where we measure conductivity of residual metal, actually impedance. After that, the next step, we remove the rest of copper to and we have endpoint, which is optical. And after that, we remove tantalum and disconnect the structures. This is the result. Why do we need so long, so expensive way to deposit more and after that to remove it? Very easy. It comes from electroplating because we don't know to deposit copper by uniformly. The wafer is connected, you see, the seed layer is here. We connect to the bevel of the wafer, this is a contact where we connect it to electricity and we place into electroplater. And there is the anode, huge anode made from copper, and we deposit copper. And this is what we typically get. This is the thickness of copper close to the contact, close to the bevel is very high, and in the middle is much thinner. And therefore, we need to create a very thick layer, and after that, remove everything we don't need. Why it's happened? We will understand, yeah, because of resistivity of this seed layer, and actually voltage is lower here and high here, and current density is lower here, and current density is high here. How to solve it? If you go to AI, to ChatGPT, if you it will say you need to deposit a lot, and after that to remove everything you don't need, or you can add dummy anode, dummy cathode in order to take some amount of current and reduce this this thick layer. This is what actually done, but it's not engineering solution. I don't like it. It's not innovation. Since we deposit what we don't need also on dummy cathode, it's not innovative solution. Let's start to analyze it. Problem statement. The next step is problem statement. We should state problem, and we state it in 5 steps, and we have helper. Helper will read everything and give its vision, why it's happened, not why it's happened. And this is just shorter explanation what we described in the overview. So we can accept it and start to argue with this. The next step is disadvantages. Why it's not good, because maybe it's not so bad when we have not very good uniformity. And we also can ask for help and pick up something, yeah. The radial non-uniformity deposit thickness, okay, we can pick some. Yeah, all of them is okay. And so on. The next one is ideal final result, which is what we are going to have. So reduce material, achieve uniform copper. This is what we need. And gaps, what is well, what prevents us from this? Inadequate understanding, right? Lack of innovative, yes. Yeah, all of them are relevant for us. And as a problem to solve, we picked up current copper electroplating process in the semiconductor manufacturing suffers from radial non-uniformity. And also we can get it from helper. But what's important, what we learned from this page, we learned, I think, very important thing, that this is not incident. It is not excursion. It is not somebody's mistake, malfunction. This is a failure by design. The equipment designers, equipment producers knew about this, and this is what they did. They created equipment that produced not uniform deposition, not uniform layer of copper. And semiconductor manufacturing accepted it and tried somehow to fight with this, but accepted it. This is not the excursion. It's not problems that suddenly happened. This is a failure or problem by design. So let's go to creative thinking tools. By the way, we have 12 tools. We can ask for help. Which tool AI will recommend? Okay, it recommends 5 whys, cause and effect chain, functional modeling. Let's go to cause and effect chain, but I prepared something. Yeah, here is the explanation, what we are going to analyze. This is their explanation of our system. And what is our pain? That sickness is not uniform, and sickness material is thicker on the edges and thinner in the middle part and in the center. And we can try to build diagram. Okay, I just already started. After copper electroplating, the copper deposit on the wafer is not uniform. Why? Why? We can ask for help. We can ask for help. Should read everything. It's a lot. Okay. It's high sheet resistance, C, and causes IR drop. Electrical count. Okay, yeah, we can keep it. We can take it. What is maybe some more reason? Why? Electrical current insufficient mass transfer. Uneven electrolyte. You know, for instance, let's pick up this. I just make it shorter. You know, I want to add manually electroplating equipment does not allow to make uniform deposition, uniform copper deposition. Yeah. Let's say does not allow. Okay, allow. Okay. And I want to add some more that the process recipe does not provide uniform uniform deposition deposit of copper layer. Okay. Okay. This. Okay. Let's have a look. What we have more? Why is this? High sheet resistance. Okay, thin copper layer. Okay, inherent high resistivity, non-uniform. No, it's uniform, but thin layer. Okay, it's thin layer. This one. Why this? Mass transport. Okay, inadequate wafer rotation. Electrolyte. Electrolyte viscosity, I don't think so. Okay, let's pick up this. And what about this? What about equipment? What about equipment? Oh, very good idea. Something with anode. By the way, why do we need such a big anode? Anode with the size of the wafer. Let's pick up idea. Document idea. Use smaller anode. Anode. A smaller anode. Uh, for electrolysis. Yeah. Okay. Good idea. Why this one? Let's pick up something. So it's actually users didn't do it. Contact DC current application fails to compensate for radial. Okay, inadequate organic. Let's pick up this. So we separated some directions. We learned something. We even uh, documented one idea. Let's go to next two. Let's pick up. Let's pick up. It was recommended 5 whys. Let's pick up five whys. 5 whys. Okay, 5 whys. Oh, just a moment. Maybe I. No, just. Okay. So let's pick up 5 whys. Uh, just for example, let's non-uniform of copper deposit on the silicon wafer at copper electroplating. Okay, why? Why it's non-uniform? We can ask for help also here. Thin layer, electrical contact, the quiet. Okay. Inadequate uniformity of current distribution. I would like to first write because more copper deposited on the periphery of the wafer and less copper is deposited on the mid and in the central part of the wafer. Okay. Okay. Let's have a look what he will say. High current density. Yeah, sure. Oh, IR voltage drop in resistive C. Yeah. Why? Why? Capacity is to see in electrical contact applied on the bevel of the wafer. Okay, let's pick up this one. And the final one, I would say what's happened that electrolysis strongly depend on the voltage. Too high sensitivity of the deposition to be applied to the applied voltage. All right, and I can mark it as a fundamental reason for problem, and I have these additional fields to think about solutions. I can add solutions for each step. For instance, here I can let's have a look what he can propose. Implement constant current electroplating mode using feedback. Optimize electrolyte additives. Integrate real time. Okay, or something. For instance, this one not very good. Here, electrical contacts are applied only on the wafer bevel. Okay. Redesign the wafer holder. No, come on. Introduce the conductive, okay. Adopt backside. Okay, something we can apply. You see, solutions are not very, very interesting. Let's have a look. Optimize PVD seed layer. Okay, seed layer is made by PVD. Yes, maybe we should modify a seed layer deposition. Okay, more copper deposited on the periphery. What's happened here? Okay, I mean pulse. Okay, pulse reverse electroplating. So we deposit and we dissolve. We will dissolve, let's say, which has a high current density. Yeah, it's a good one. Yeah, pulse reverse electroplating mode. It will take longer time, but it might help. And this one, non-uniform, what he can tell us. Redesign anode configuration, incorporate enhance deploy inline wafer mapping, XRF. I don't like none of them. I don't like it. I don't like it. Learn how the deposition occurs. Okay, this is, I showed you for example, just as an example. This is very, you see very, very small amount of steps. And we already made this work, and we made much more step. Oh, sorry. Much more steps. It's 5 Ys is just a name. We should use as more as possible steps, and we generated a lot of different solutions. And what we learned overall from this that the deposition is strongly depends on the voltage. Strongly depends on the voltage. Why is it? Why we cannot change it? Uh, Based on these two tools, we generated a lot of ideas, and you all can see here on the on the idea manager, and the ideas first to increase temperature. To increase temperature, when we increase temperature, we make interaction more fast. Reduce diameter of anode. This is what we told about. Increase voltage of the process. Implement pulse current, pulse and reverse current. Begin with copper deposition with the electroless process. We can make electroless. We can start with electroless deposition and make this seed layer thicker, and after that continue with electrolysis. Yeah, insert the separation net near the wafer to reduce diffusion ions, so somehow impact on the diffusion. So we can, you see, we have a lot of ideas, and they all can help, but they not they don't make some dramatic changes. We should understand the process, and to understand why it's happened. And we used a functional model. I like functional model, and we used functional model. So here we describe the process again. And this is a picture of an electroplater. It's not exactly like this, but it's okay. And we created functional model. So the product is a copper electroplated on the wafer, and I separated a seed on the periphery and seed layer on the mid and the center of the wafer, and copper plated here on the periphery, and copper plated on the mid and central part of the wafer, because it's different. We have anode, we have electroplate cell, we have chemistry, which are sulfuric acid, water, copper sulfate, some additives, and we have copper ions, and we have contacts, wafer, and we connected it with functions. With the function, electrolyte consists of water, sulfuric acid, and it keeps copper sulfate, it keeps water, it keeps sulfuric acid, it keeps ions, it keeps additives. If you see, there is no harmful functions here because generally we can assign harmful function. In our case, no harmful function. Everything is useful. First of all, when we created this functional model, we learned how our system operates. And we learned a lot. The second, we can go to the ranking, and ranking a platform will automatically calculate the main parameters of this system, this electroplater, which is less important. But what's important, it calculates functional and problematic rank. And have a look. Copper ion, cation, the most functional and the most problematic in the same way, in the same time. So not seed layer, not contacts, but only copper ion. So it makes us think, leave aside everything.
Anatoly, for some reason we can't hear you. Anatoly, hello?
Can you hear me? Yeah, I'm so sorry, guys. When it's stopped,
When you just started with the ranking
with the
explanation.
ranking. So I'm
Yeah.
so sorry. I'm so sorry. So a platform, the platform is calculating the main parameters of the system, which is less important currently. But what's very important, it calculates functional and problematic rank for each component. And what's interesting, that copper ions are the most functional and the most problematic in the same time. So no contacts, no thin layer of seed layer, no electrolyte, nothing, only copper ion. And we have to think, we have to leave aside everything and start thinking how copper ion behavior can generate a non-uniform deposition. Let's try to remind what's happened in the electrolyte. This is what we learned in primary school. Yeah, copper ion should move to the should be delivered to the surface of the wafer, and this step is called diffusion. And the second step is interaction itself. And we should, a copper ion should pick up two electrons and get converted into metal, into copper metal. Ohm's law is not working in these systems. This is the second type conductor. What is working? Let's go to this volt ampere characteristic. It looks like this. Looks like this. What does it mean? We have this area that calls kinetic mechanism, and this area calls diffusion mechanism. What does it mean, kinetic mechanism? It means that discharge is going very, very slow. And if it's slow, this is what manages all process. So diffusion is very fast. Delivery of ion, copper ion, is very fast, but interaction is slow. Therefore, we can change voltage and we change current. The second part of this curve is called diffusion. It's diffusion mechanism. It means the diffusion is very slow, goes very slow, but interaction is very fast. And all process is defined by diffusion. What's interesting now, what's happened with the process? The process is done on galvanostatic mechanism. It means the current is constant. And it means we're working here in this area. And this area is very sensitive to voltage. What my meaning is, for instance, if the current is here, it could be current on the bevel is here, while current in the center of the wafer will be here. And overall, all current is okay, as we described, but it is different according to the resistivity of the seed layer. We should move process into the direction where there is no sensitivity to voltage. And this is this direction. So if we make electrolysis here, we will have a uniform layer, because there is no dependence current from voltage. But of course, in the regime of galvanostatic regime, we cannot be here. We should get switched into potentiostatic regime and just keep voltage here. So what I see from the very beginning, it was made mistake. A producer of electroplater for semiconductors made mistake because they keep process with their galvanostatic regime, and they should be potentiostatic regime. So generally, what we separated first, increase temperature. When we increase temperature, we increase the rate of integration, that we also move to this direction. The second, we can reduce the diameter of anode. and we need to increase applied voltage. But if we switched from galvanostatic to potential static regime, we will solve this problem. So this is what I learned from this situation. And again, this is not excursion. This is problem. This is failure by design. So now I'm ready to answer your questions. Well, please comment.
First of all, thank you for the presentation from me
By the way,
personally.
was it clear regarding this explanation? Here we have very strong dependence of current from voltage, and here there is no dependence of current. So we should be here and not here. That's all. Oh, everyone is sleeping.
Questions, comments? Dean, thank you for the reaction.
Yeah.
It's
Guys, I'm sure there are a lot of such things that makes our life and our work very difficult by design. Just engineers in the producing equipment for semiconductors didn't do good work. That's all. Didn't do good engineering.
Can I ask, Anatoly?
Yeah, sure, sure.
Yeah, thank you for this hands-on workshop, online workshop. I have a personal experience with cause chain, cause effect chain tool, and I was working for my task for thermal management for a cold plate.
Mhm.
And what I ended up with was very similar what you showed, what you presented, and where you ended up today. Something very general, and it didn't lead me to any specific design or something that I can take out and move towards to uh, quantitative analysis. Can you probably comment on it? Is it a drawback by design of this tool? Or
No,
is it my misinterpretation
yeah,
for this tool? Mm.
yeah. It's yeah. First of all, thank you for your question. You know, this tool is not easy because an effect chain, and it requires very hard work. And the question, what is your expectation? In this particular case, I wanted to pick up something like I picked up the idea with anode. Indeed, why do we need such big anode? And I stopped there. I can generally I can continue with this, but I left it for 5 mice. But generally, it can be continued, and I have another examples with a huge tree we built, and we found very interesting, very uh, unexpected things. So look, tool doesn't solve problem. Tool makes us think, and this tool, this is what it's doing.
Yeah, understood. So it's about expectation management. Got it,
Yeah.
Anatoly. Mm.
Mhm.
if I may, I wanted to add something to that, to Anatoly's answer, is also very much related to expectations. And yes, we have AI embedded in here and some AI help. Yeah, but some people do expect quick quick and dirty answers from AI, which they get, right? But they're not necessarily good answers because AI is a one big statistical machine. So it relies on the previous well-known data, so it can't really produce something for the future. And that's why we always promoting, listen to AI, but then start arguing with it. Because the same as you would sit in a room, first ideas that come in brainstorming sessions, they usually well-known, somebody did something in the past. It's exactly the same situation here. It's only in the argument process in argument process you can get the good answers, good solutions. But you can only argue if you understand the system well enough, right? That's the key. Yeah, that was just my 5 cents here.
Okay, thank you, Alex, for the input.
Any other questions, comments?
Yeah, I have one more, but I can wait for and
No,
give a
go
chance.
for
Okay, ask it
go
now.
for it.
Okay, I go for it. Uh, uh, it's not a comfortable question, but I'm so curious to answer or to ask for it. When I was looking at this process, five whys and cause effect chain, I uh, I thought that probably I can just use a standalone uh, chat with an AI and do a similar thing. Like I tell it, we are working now with a cause effect chain, and we
Hmm.
continue the discussion in the chat. I love your platform. I don't want to criticize it, but I just want your comment. How does your AI, embedded AI, differ from from my scenario, from what I just described, or it's just a convenient visual like desktop application, your platform, what it is now, and one can do a similar discussion and getting some hints from AI just in an AI tool as a standalone tool in the chat.
Yeah.
So Alex
I
can
can I
answer. Yeah, yeah.
Yeah, I can jump into that. So there's two parallel thought streams here. First of all, whatever tools exist in PRIZ platform, they first and foremost built for humans, not for AI, not for the machine, right? So basically, if you decide to turn off AI, and by the way, you can go into the settings and click the check mark and say, I don't want AI, and that whole thing disappears, right? So it's built for humans and humans only. And I think that's the biggest differentiator here because some companies will say we don't use AI, we see risk in it, so on and so forth, even though they're getting out of that notion of line of thought, right? But the biggest thing that if you compare AI to AI, right? At some point when you're using, for example, ChatGPT or Gemini or any other tool out there, at some point, the further you go, and you can imagine that some of these projects they can be very long, right? It's not a conversation of 5 minutes or even an hour. It can be 5 months conversation. So in a traditional AI or available tools inside AI, they will start losing context, whether you want it or not. What happens here in the system knows it has access to all of these details and all of that data in a way that the agents that embedded in the system, they can pick and choose the right information to go after to try and answer your question. And it's not a gigantic conversation, endless conversation that you started somewhere and then, you need to keep track of it. I can compare it to the same conversation of many people in the room, right? You get in a conference room with whatever 5 people and start trying to solve the problem. And you sit in that room for a week. You will forget what happened in the first day, right? But you will forget it actually much faster than a week after, right? You will forget in 2 hours what you talked at the beginning. This is what these AI in the platform actually helps the most because it does know, or at least it has an attempt to grab the right information. Same, for example, in cause and effect chain, right? It relies on the entire write-up of what you had in the background. It relies on your problem statement. It relies on the tree that you already built in cause and effect chain, right? Imagine yourself, you're putting everything on a board, like on a physical board, right? And imagine you created a tree of 50 nodes. Try to reason with that. It's really, really, really hard, right? It's just a human being, it's really, really hard. But AI is capable of saying, okay, I have all of these reasons already written down, so I don't need to worry about them. I just need to worry about this particular chain, make sure that I may or may not have a correlation, but ideally I shouldn't. Know what I can come up with, right? So it's these little details that we typically not thinking about, but they are the ones who that act as a barrier to solve a problem in an efficient way. It's purely cognitive load.
Oh, yeah,
So,
yeah. Understood. This I didn't know about the platform. Nice, nice thing. So it's not a
Uh,
simple
mhm.
integration. Mm.
from
No,
my
no.
point of view, for me, AI is just additional member of team. Just he's
Mhm.
saying something not very clever, by the way, but it may give some good ideas and good directions for thinking. By the way, I just forgot to show you something that we teach our AI regarding creation functional model. Let's ask him to create. We teach him how to create functional model. He said it's okay. Uh, yes. It's thinking.
And by the
Yes.
way, this is something that important to understand as well. It proposes something. It proposes, it can very well execute kind of standard tasks. And standard tasks, like a very well-known tasks or, common knowledge things, it can do that. So that's why what you will see here, what Anatoly shows, it will create kind of a baseline of well-known things, but a human being needs to take it from there, right? And still, it takes time, something that usually will take hours to do. It takes a minute, minute and a half-ish, right? So let's hope it actually produces what it needs to produce. This is probably the heaviest functionality of agentic functionality that we have in a platform. I think we need to start telling jokes while it's doing its thing to keep people entertained.
No, no, no. It's intriguing what it shows.
Ah, some people just give up and leave.
What's happened? What's happened?
So, a comment I would like to make about the AI is you think AI, or some people might think AI is one thing, it knows everything. Actually,
Hmm.
there are a lot of different AI bases. And I find that the AI is sort of like watching YouTube. You get all
Hmm.
these people on there giving answers to a question. And if you, the human, don't
Oh,
have
I'm
sense
sorry. Something.
to decide which ones make
Something.
sense, you're in trouble.
Hmm.
I think it's.
Just click again. Just click again.
Okay.
It just takes a longer time. Sorry, David, for interruption. But yes, for AI, just to continue the thought, the AI itself becomes smart, quote unquote, not because of AI itself, but because of the tools that we're attaching to AI, right? A simple example, if you ask AI to calculate a mathematical equation or whatever, 2 plus 2, what is it equal to? Technically, it can do that, right? But it can also hallucinate and saying, ah, it's actually 5. But if you give it a tool called a calculator, where you provide it, you know, give me two numbers, I will give you provide you some of them. It can actually choose very well the tool that it needs to use, and that tool doing the job really well. So the smartness is coming from the tools. Same that we basically built here. It's the tools that know how to do particular things in the platform. And the AI basically becomes kind of an orchestrator for these things.
I don't know what's happened. It was
It's
working. Okay. Yeah.
maybe the provider is hmm, sorry about that. Yeah, so the problem with that again, we're still working on this particular functionality to improve it better, but the idea behind it that we need to improve the speed on that because there are certain limitations of how much we can wait on the line before the basically connection is dropping. So it's a few small technical difficulties where we still need to solve. All right. Any other questions while we wait for that? Oh, Dean was asking, Dean, what did the seed layer say to the copper anode? Let's hang out.
Can you see? Guys,
Yeah.
it's not ideal. But this is some basis that we can start to work with, and we can walk in two directions, in two ways. By the way, what I see, it didn't separate on seed on the periphery or seed on the central part. We should add it. And there are two possibilities. We can modify the model, or we can modify the description. And when we modify description, the model will be updated accordingly. Okay. But this helps a lot. This is what we can start with. And because to create functional model, it takes hours. In this case, you have already basis, and you can have a look on the. It says seed layer, but it's not ideal. It's not still not. We should work on this model, but it defined seed layer, right? It's so by this way we already have something to start working with. This is what my meaning is. And again, if you ask AI, what should I do in order to ensure uniformity, it will say deposit more in polish or add dummy cathode. But I can say, please create functional model. And after that, we can ask him, now, what do you say? Or what I will say. And this is different. This is the main difference. We should, what my meaning is that AI needs creative thinking tools in the same manner as we do. Okay, thank you guys. Sorry for it took some longer than we expected.
Thank you for your time. We'll publish everything and I'll stop the recording.
Anatoly,